Okay, let's move on now and talk about addition rules for probability. As you can probably guess, the calculating the fairly simple probabilities, like we saw last time, are useful, but as situations get more complex, it might become useful to calculate probabilities for more complex scenarios. Um, so let's talk a bit about some properties of probability. The probability of any event is going to be between 0 and 1. An, an event can't be over 100% likely to occur. Uh, because the way we calculated things was the number of outcomes that hit the event space. Sorry, the number of outcomes that fit in our event over the total number of outcomes. That cannot be greater than 1. We cannot have more outcomes that fit the event than are in our overall probability space. If we do, then we've got something seriously wrong with our entire setup. The entirety of the sample space is going to equal 1. Um, if we look at the sample space, the probability that our answer is in the sample space is 100%. The empty set, as they say there, is 0. Um, we're also going to define something called the complement. So it's the set of outcomes that does not fit in our event. So in the card example we gave in section 4.1, we had 1 queen of spades and 52 cards. That means the complementary complementary event is 51 cards that are not the queen of spades. So let's describe some complements. The complement of choosing a red card out of a standard deck of cards. The complement of the if we have 15 students in a class of 31 that are out with the flu, what is the complement of that event set that's 15? If 91% of phone customers use a particular phone company, what is the complement of that set? Okay. Since there are 52 cards in a deck, each deck contains 4 suits. 2 suits are red, 2 suits are black, typically. So it's 26 cards of red, 26 cards of black. So if you've got 26 red cards, the complementary set is the 26 black cards. Out of 31 students, if 15 are sick with the flu, the remaining 16 are not sick. That is our complementary set. If 91% of the customers use a particular phone company, the complementary set is what's going to add up to 100%, which is 9% in this case. So there's a nice convenient complement rule for this. The probability of the event plus the probability of the complement equals 1, or 100% if you want it in percentage terms, not decimal terms. Right, so we used this a second ago with the phone company example. If my set is 91%, the complement will be 9%, and I can get that by subtracting that 91% from 100% because of this rule right here. If I wanted to calculate the complement for the odds of rolling a 6 with a single die, that's a 1 in 6 for the 6, and the complement is going to be every other value, which is going to be 5 and 6, so that will add up to 1. It is sometimes easier to calculate the complement than the probability itself, and you can just calculate the complement and subtract it from 1 and get the probability itself. It's just rearranging that equation we saw on the last slide. So if you get, for example, stressed out that there's a 35% chance you'll fail your upcoming test, what is the probability that you'll pass? Because that's a less stressful value. So 1 minus 35, or sorry, 100 minus 35 if you want to keep it in percentage, 1 minus 0.35 in decimal form. That will give you a 65% probability that you will pass the test. There's a 5% chance that none of the items on your scratch-off ticket will be a winner. What is the probability that at least one will win? Take a moment to do that yourself and move on when you're ready. We already did that, so I'm not going to go over it other than to pause here so you can, if I talk too fast or something, you can write that down. Okay, again, probability is going to be 1 minus the probability we're after. Let me rephrase that. The probability that we want, the probability that there's at least one winner, is going to be 1 minus its complement, the probability that there are no winners. 1 minus 0.05, that's 5%, is 0.95, which is 95%. I've been assuming everybody can go between decimal and percentage pretty easily. If that's not the case, I'd appreciate it if you would all let me know, and I'll slow down on that and double check that I'm explicitly stating what I'm doing every time. Okay, so if we've got a pair of dice and standard six-sided, what is the probability that neither dice is a 3? This is probably a pretty good example of where it's easier to calculate the complement to that. It's easier to calculate the probability that we have a 3 as one of the die, and then back calculate the probability that neither is 3. So go ahead and take a minute and do that, and move on when you're ready. Okay, so let's list the outcomes that do have a 3. And then we're going to double check that things add up and make sense. So here's the ones that have a 3. We can have the first, so we've got the first die and the second die. We can have, if the first die's got a 3, second die can have a 1, 2, 3, 4, 5, or 6. If the second die has a 3, the first die can have a 1, 2, 3, 4, 5, or 6. You'll note this one where they both have a 3 is in both sets, so we don't want to double count that. That'll be important in a minute. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That 11 possibilities that have a 3. I do not remember offhand from the last session how many total possibilities there are. 6 of each. I'm thinking 36 if I'm thinking correctly. Yes, 36. 36 possible ways. You can have 1 through 6 possible on each die. So we have 11 out of 36. Again, all of these probabilities are the number of things that fit our event set. In this case, it's the complement of the event set we're actually after, but it fits that event over the total number of outcomes. So if we subtract that from 1 to get the event we actually care about, is how many aren't a 3. So 1 minus 11 over 36 gives us 69.4%. Okay, we also have this nice addition rule. So if we've got two events, we'll call them E and F. The probability that either event could occur, either E or F. So if I was after things that had, rules of a paradise that had a 3 or a 4, for example, I could use a formula like this, calculate the probability of having a 3, calculate the probability of having a 4, subtract off the probability of having a 3 and a 4. So as you saw with the example with the where we didn't want to double count the 2 3s, um, I could think about, so in that example we've got the probability that die 1 is a 3 and the probability that die 2 is a 3. We need to subtract off that die 1 and die 2 being a 3, so that we don't double count something. Right here. This grouping here is the probability that die 1 has a 3. This one is the probability that die 2 has a 3. We subtract 1 off for this so that we're only counting it once. And that is all we're doing right here. We're subtracting off what we would otherwise double count. So let's do an example. We've got somebody out condo shopping. They've got 17 available properties. We've got 6 that are close to the subway, 7 with low maintenance fees, 5 that are near green space, 2 that are newly renovated. And we've got some combinations. We have 2 that are close to the subway and have low maintenance fees. 1 that's got green space and newly renovated. So, what are the probabilities that the first randomly selected condo to visit is either close to the subway or has a low maintenance fee? Alright, so I'm going to go back for a second so you can get the information, do the calculation, and move on when you're ready. Just give you a second to make sure you've got these values. Go back so you can get these values. Okay, and move on when you're ready. I've got alright. Might seem like if you added all the numbers, there'd be more than 17. So we've got 20 properties with single characteristics, but of those, 3 properties have 2 characteristics each, so that's 17 properties. So it's kind of the same calculation. We've got 20 buckets, but 3 things fit in 2 buckets, so we're subtracting off that second category to get the individual numbers again. The exact same concept. Subtract off what would otherwise be double counted. So really, one of the key words here is or. And that's a key word you should look for in things like this that tell you that you're going to be using this addition rule. Add the 2 probabilities and subtract off what could be double counted. So, close to the subway, 6 of 17. Low maintenance fee, 7 of 17. Things with both is 2. So that gives us 11 of 17. So 64.71% that chance that the first place we visit has both. Okay, so let's talk about Senate votes. Um, we've got a health care bill. 23% of the Democrats vote for, 43% of the Republicans vote for, 2% of the, or sorry, 2 of the, not percent, 2 total independents vote for. Got the 21 Democrats voting against, 7 Republicans voting against, and 4 independents voting against. Is this going to add up to 100? There are only 100 senators. That's 50, 73, 94. Yes. Okay. Sorry, I thought it was going to add up to more than 100 for a second. So if somebody stops a random senator after the vote, what is the probability that this senator will be either a Republican or have voted against the bill? So there's our key word, or. So take a minute, think about how to do this, write it out, get your solution, and move on when you think you're ready. Okay, so there are 100 senators. 53 plus 7 is 50 Republicans, right? There's our Republicans, 53 plus 7. And voted against, so we've got this column, 21, 7, and 4. So 21 plus 7 plus 4 is 32 that voted against the bill. 7 senators are both Republican and voted against the bill, so those are the numbers we're going to be needing. So Republicans, 50 of 100. Voted against, 32 of 100. Minus Republicans who voted against, 77 of 100. Gives us 75 over 100, or 3/4. So it's 75% chance that the first person the lobbyist talks to is either Republican or voted against the bill. So if we've got a pair of dice, what's the probability of rolling either less than 4 or a total of 10? Okay. So if we think back to, so we want less than 4, not less than or equal to. So we've got value of 1, value of 2, a value of 3. Sorry, pair of dice, we can't have a value of 1. So we've got a value of 2 or a value of 3. Right. Probability less. Okay, there's our formula again. Probability less than 4, probability of 10, less than 4 and 10. Is there any chance we can have something that is less than 4 and add up to 10? Well, no, that's going to go to a 0. So we can put a 0 in there. Let's move on. So less than 4, we can have a pair of 1s, a 1 and a 2, or a 2 and a 1. So there are 3 out of 36 that'll give us less than 4. There are 2 5s, a 6 and a 4, and a 4 and a 6 that will give us a total of 10. So 3 that will give us 3 out of 36 that will give us a total of 10. Right? So 3 out of 36 plus 3 out of 36 minus that, there's no chance that we'll have both. So that gives us 1 in 6 chance of either less than 4 or 10. So since there's no chance we could have both events, they're called mutually exclusive. They don't have any outcomes in common. You can simplify the addition rule for mutually exclusive events, and it's just by dropping that subtracting off term. So you can either try to remember this or just know that mutually exclusive means that the probability of both is 0. Um, the probability of E and F as a group is 0, and use that. Whatever's easiest for you, they are the same thing. Okay, so let's do an example with mutually exclusive event. Got a kid named Caleb who's buying his first car. He's got 4 choices, and his friends have started to take bets on which car he'll choose. They've given each car a probability based on how likely they think Caleb is to choose the car. One of his friends is betting that he'll choose either the Toyota or the Jeep. What is the probability that he's right? So as you can guess, there is no chance that Caleb is going to buy both the Toyota and the Jeep. He's only buying one new car after all. Right? These are the probabilities his friends assigned to the cars. 40% in the Toyota, 10% each on the Ford and Honda, and 35% on the Jeep. They think Caleb's going to be doing some off-roading. Okay, so let's assume that his friends had good guesses and fairly accurate. So we've got the probability for a Toyota at 40% plus the probability of the Jeep at 35%. Should be a 75% chance he will get the Toyota or the Jeep. Okay. So we've got truck driver. There's these probabilities that a truck driver will fill at any particular brand of gas station. So what are the probabilities that the truck driver will refuel only at one gas station over his trip, making all of these mutually exclusive? So what are the probabilities he will end up choosing Chevron, Exxon, or Shell? They're mutually exclusive, so we can add the individual probabilities together and not have anything subtract off because there's no chance he'll stop at Shell and Exxon and Chevron, and we get 75.39%. Okay.